Today, our plan is we're going to be jumping ahead to section 5.3. We'll circle back to 5.2 in a little bit. Now, hold on. Ah! I should have saved this for Halloween, but it's the scariest word in the math class. Prove. Now, shh. Now, all of you having like post-traumatic reactions to your geometry experience, have no fear. The proof that we're going to be asking you to do for these identities, not the same as like the 2-column proof that you did for geometry. In fact, this will be not significantly different than the simplifying that we did in the previous lesson. And in fact, it'll be almost easier than the simplifying we did in a previous lesson, because it's kind of like you have the answer already. So your job is going to be to like fill in how we get from start to finish, but it's basically like a simplifying problem where you have the answer already. So before we kind of dip in and start doing some examples, I want to just kind of start by giving you guys a couple of general strategies that are often useful when working on these kinds of problems. So number one, when we do these sorts of problems, you're allowed only to work on one side of the identity. So you pick one side to work on. You cannot do things to both sides. You cannot cross multiply. Can't do stuff like that. You can work on one side and you can go until you end at the other. In general, you probably want to begin with the more complicated side first and work towards the simpler. Now, we'll see instances where, you know, like maybe you choose not to do that. But I want to point this out, that regardless of the side you start with, all of these are possible from either side. They are true statements. You can start on one side and end with the other, regardless of which side you choose. In general, though, starting with the more complicated side is usually easier than starting with the simpler side. It's much more intuitive to cancel things off, to take something complicated and make it simpler, than to like build stuff on to take something simple and make it more complicated. We're much more practiced in mathematics, like simplifying and reducing and combining like terms and doing things like that, than we are like, you know, like saying, oh, like, you know, 3 is the same thing as 8 minus 5. It's like, okay, but like, why would I ever want to change 3 into 8 minus 5? That would be kind of, if you're starting with the simpler side and building backwards, that's kind of what you end up having to do sometimes. It just seems less intuitive to students. In general, if you get stuck and you're not sure what to do, convert everything into sines and cosines. 4 is combine fractions by getting a common denominator. Make sure that you're looking for those common denominators. 5 is the difference of two squares factoring pattern. You remember this from Algebra 2, that a squared minus b squared is equal to a plus b times a minus b, is going to happen frequently. That'll be something that pops up frequently. It's often a very good idea, if you see half of that difference of two squares, like an a plus b, to just go ahead and multiply like the top and bottom to make it with an a minus b to get that a squared minus b squared. Because oftentimes that'll unlock a Pythagorean identity to use. Okay, so that's going to happen a lot. And then number 6 is to simply always be looking at where you're trying to get to and use that as a guide of like, what might I want to do? What identity might I want to use here? If I have tangent, I can rewrite it as sine over cosine, or I could write as secant over cosecant. Which one of those two, or 1 over cotangent, which one of those 3 options would be the best one to use? Oftentimes looking at where you're trying to get to will tell you. If where you're trying to get to doesn't have a cotangent in it and it has no fractions, 1 over cotangent is probably a bad option. If you see sines and cosines in the end, maybe that's a better route to pick tangent to be sine over cosine. You kind of get what I'm saying? All right. In general, though, the process that we're going to be using is going to be the same as what we've been doing when we've been simplifying. We're just going to be doing this the same kind of steps. So again, typically the steps are going to be either doing an algebra thing or applying an identity. So the first thing you'd want to do is you want to look at your identity that you're given. Here we're given tan x plus cotangent x equals secant x times cosecant x. Oh my goodness. And I want to decide, for starters, which side I want to work on. Which one of the two is more complicated? What does Mr. Kulik even mean by more complicated? So if I look at the left-hand side, I see that I have 2 things and they're added together. If I look at the right-hand side, I see 1 thing that consists of 2 pieces added together, right? In general, addition, we're going to think of as more complicated than multiplication. If it's me, I would choose to work on the left-hand side because I see 2 things on the left and I see 1 thing on the right. The technical definition there is terms. The left-hand side has 2 terms. The right-hand side has 1 term. 2 is more complicated than 1. I would start on the left. Everybody feel okay there? All right. So my goal here is to turn tangent plus cotangent into secant times cosecant. Now, there's no way I can add tangent and cotangent together as they're currently written. So I'm going to go and look at my identities. So I look at my identities for tangent and cotangent. If you don't have your identity sheet out with you, it might be a good idea to take that out so you can follow along as I'm kind of talking about things. For example, for tangent, I have 3 options. I can rewrite tangent as sine over cosine. I can write it as secant over cosecant. Or I could write as 1 over cotangent. Not immediately clear which one of those 3 I would want to use. But if I look at the end, where am I trying to get to? I'm trying to get to secant times cosecant. So maybe I think, well, I'm going to pick Q1 and I'm going to turn tangent into secant x over cosecant x because I see that my final result has secants and cosecants in it. Not an unreasonable thing to think. Everybody's okay? Similarly, we'll do the same thing using Q2 for cotangent. And write that as cosecant over secant using Q2. Everybody's okay so far, so good? Okay. Just as an aside here, when I write my identity proofs, typically I go vertically down the page, where the right-hand side is always just the same thing, but I don't really ever write it again, as opposed to my simplification proofs where I just go from left to right, one equal sign after another after another. Is everybody okay there? All right. So if I look here now, I have everything in terms of secants and cosecants. I think, okay, that's probably pretty good. But I have these two fractions that I need to add together. Well, if I have to add fractions, what do I have to have? Bless you. Common denominator. If I look at these two fractions, what would the common denominator be? Cosecant times secant. Wonderful. So I'll take the first fraction, multiply it by secant over secant. And I'll take the second fraction, multiply it by cosecant over cosecant. Oops. So I just made a common denominator there, so I'll just write CD. So far, so good?
Could you do like cosecant times over cosecant for the first one or no? Like, does it matter which one you do? Like, could I do like cosecant over cosecant?
Sure, but you're just going to end up right back where we started. Right, if I multiply the first one by 1 over cosecant. Is that what you're saying?
No, like cosecant over, like, see how you put like secant over secant? Can I do with the denominator or with the...
Well, when you made a common denominator, you had to do like this, right? You had to add, right? The rules are the same. You can't do like, I'll multiply this one by 3 over 2 or something like that. You can't do that. Is that what you're asking? Okay. So if we make some common, or we've made our common denominator, so let's go ahead and just like multiply everything out. So on the top I have secant times secant, that's secant squared. And then plus cosecant times cosecant, that's cosecant squared. No. Yeah, addition, can't do that. Can't reduce there. So I don't know, combined like terms, I guess, is what I did there. So if I look, there's nothing more to combine, right, algebraically. I can't reduce, as Max we just pointed that out. So maybe I look for an identity here. You guys see anything identity-wise to use? Yeah, so you see the squares. Maybe we look at the Pythagoreans. Yeah, since I have a secant squared, I could use P3 and write that as tan squared plus 1, but that seems like that's getting me further away, right? I think I want to hang on to the secants and cosecants. That's what my answer is supposed to be in. What does it look like here? It just doesn't look like I'm making any progress, right? I'm just going to scrap this and go, okay, well, that didn't seem like it was working very well. what if I go back to this Q1 and Q2 choice, and instead of using the secant, cosecant versions, if I use sine and cosine versions, let me just try that instead. Now, could I have still kept going and gotten this to the final? Yeah, but it didn't seem like I couldn't really see the finish line there. So I just said, well, like nuts to it. Maybe it's going to just be easier to just start over. And then we'll make a common denominator the same way we did before. Right? No surprise here. We had the two fractions. So there's making the common denominator. Do it the same way, right? Just we're using sine over sine and cosine over cosine. When I combine my like terms, I have sine squared plus cosine squared over sine x times cosine x. And this is looking a lot more appealing to me. What do I notice here that I could use? Be staring at you right in the face. Yeah, it's sine squared plus cosine squared. That's just P1. That's 1. All right. And then, aha, I'm going to use this trick Mr. Kulik's shown me before, where I like kind of break this one fraction up into like the product of two separate fractions. Because I recognize 1 over sine, that's R4, that's just cosecant, and 1 over cosine, that's R5, that's just secant. And guess where we were supposed to be getting to? That was it, right? So I'll draw my little box that I filled in at the end to mark my proof as complete. And I'm done, right? If I go back to the beginning, what was I trying to get to? Secant times cosecant. That's what I have, right? Yay! Or I guess circle it here. Now, Mr. Kulik, in the beginning, did you like just screw that up? Like, why did you just throw out the baby with the bathwater there at the beginning? Well, I did it on purpose. I wanted to show you that, like, while there is no wrong way to do these problems, if you go for a little bit, you wade in and it doesn't seem like you're making any progress, there's nothing wrong with going back and just starting over and making a different choice. And seeing like, okay, can I kind of see the finish line if I go and, like start somewhere different and make a few steps, right? So I did that on purpose to kind of demonstrate to you guys that that's a valid thing to do, that that's an okay strategy. It doesn't mean that you're doing anything wrong. It doesn't mean that you're bad at it or anything else. All right, let's take a look at this guy now. So if I look left hand, right hand side, which one's the more complicated? Yeah, they're really about the same, right? I'd agree. So just for the sake of convenience, I'm going to pick this side to start with. Yes, sir.
Would we ever like cross
So that's doing things to both sides, which you're not allowed to do. So again, when you're doing these proofs, you can work on one side or the other, but not on both. Cross multiplication is working on both because you're like really multiplying this one by like 1 minus sine times one or times cosine to both sides, and then that like is going to give you anyways. All right, so just for the sake of convenience, let's say we work on this side. So algebra identity, what should we try to do first? Well, if I do an identity, the only identities I really have open to me is replacing cosine with 1 over secant or sine with 1 over cosecant. I kind of hate both of those options because I'm putting a fraction inside of a fraction where, unless I have a good reason to do that, I probably don't want to do that. So maybe I think an algebra thing, but it's, Mr. Kulik, it's just like one fraction. What the heck am I going to do with that? Well, this is a situation where looking at where you're trying to get to, I think will make life a little bit easier. So somehow this cosine in the numerator needs to go away and is going to need to turn into a sine, right? Do I see that? Or 1 plus sine. Well, I don't have any good way to turn a cosine into 1 plus sine. So what if I just like multiply the top and bottom just by 1 plus sine? You know, like that's something I can do. I have a fraction. I know what makes me feel even better about this option is look what I have now multiplying in the denominator. That's that a plus b times a minus b. That's that difference of two squares factoring pattern. That's a good thing. That's often very helpful to me. Is everybody okay, Cameron? Of course. So let's see what happens now. So this is just like I kind of multiplied by 1. And then we'll do some combining like terms here. Well, really what we did is we FOIL, I guess. So if I FOIL out the denominator, I'm going to have 1 minus sine squared n times, or I'm sorry, just 1 minus sine squared n, right? Again, I'm using that identity, that factoring pattern, to just multiply it out, right? So rather than like foiling and like showing all my work, I just use that as my shortcut to FOIL it. We so far so good? Okay, so if I look now, I have the 1 plus sine squared that I'm supposed to in the finish line, but somehow this cosine has to come out of 1 minus sine squared, right? Is there a way I can turn 1 minus sine squared into cosines? Yes, Mr. Kulik, you can. Isn't that one of our alternate versions of P1? Right, if you look at P1 and you subtract sine squared from both sides, wouldn't P1 then say cosine squared equals 1 minus sine squared? Yeah, it would. Who sees what to do now? We're almost there, right? Gabby.
Oh, I don't know. I was asking a question about the previous.
Oh, okay.
But you were able to switch them because they like equal each other. Is that your, like for the denominator?
Cosine squared is equal to 1 minus sine squared. Yes, that's P1. Or one of an alternate version of it.
You can cancel off the cosine.
Yeah, if I cancel out the cosine, that's exactly what I need this to end up at, right? And I'm done. You guys see that? Now, just to point out to you guys, if in the beginning, instead of multiplying by 1 plus sine over 1 plus sine, I could have multiplied by cosine over cosine and still gotten to the same spot, but instead of having to FOIL things out, I would have had to factor, but also totally doable. What you're going to find over and over and over when doing these problems is there's not one single way to do any of these. Is that they almost always have many applicable ways to get to the final. Your job is just to like clearly show how we go from start to finish. All right. Which side should we start on? You be crazy. Let's start on the left side. Look at how complicated that is. I got parentheses and all that heading and all that. You could start on the right-hand side and still get there. It wouldn't be that hard, but I wouldn't want to do it. I would start with the left. What do we want to do first? If I look at my answer, do you see any adding and subtracting going on? No. Is there any multiplying going on? No. So that's the first things I'd try to do is algebraically, can I get rid of either the multiplication going on between the 1 minus cosine and the 1 plus cosine, or the adding with the 1 plus cosine or 1 minus cosine? Well, I can just FOIL that out, right? That'll, again, I noticed that like, hey, that's that difference of two squares thing. That's usually good. Let's multiply that out and see what we get. Again, I wrote FOIL. Did I really FOIL? I just used that factoring pattern that we had identified earlier on. If you FOILed it out, though, that would be fine. What do you guys see next to do?
The pattern is the A plus B, A minus B.
Yes.
There's like square root below the squares, so it would be the Pythagorean identities.
Yeah. Right? Yeah. What does 1 minus cosine squared turn into? It turns into sine squared. Oops. This is great because now I've gotten rid of all the addition and subtraction going on, right? So first step, I got rid of the multiplication. Next, I got rid of the addition and subtraction. The last thing I have to do is get rid of the division. What do you notice we can do here? Again, where are we trying to get to? Yeah, if I just apply Q1, that's going to give me exactly what I need, right? And I'm done. Oh, that wasn't so bad. All right, let's one more example from me, and we're going to use that note sheet of yours, and I'm going to take some random, not so voluntary volunteers to help us walk through some of the answers on there. All right. Last Mr. Kulik example. If I look at this, left side or right side?
Right side.
So it doesn't matter which side. It's not, one of them's not right or wrong. Okay. This is a situation where I would probably disobey the rule and probably pick the left side. Let me explain why. So if I look at this, I see, okay, I need a cosine, and I got 5 of them on this side, right? And so if this thing somehow is going to have to turn into like a sine squared and like a cosine to the 4th. If I look at this piece on the right-hand side, that trinomial, what do you think when you see a trinomial like that? Factoring. Now, I would prefer not to factor. What's the reverse of factoring? Foiling, right? Foiling, right? Everybody's okay with that? So if to go this way, looks like I have to factor. This way would imply that I should have to FOIL. Which one would you rather do, factor or FOIL? I would much rather FOIL, right? That's typically very easy to do. So I would actually work on the left-hand side here once again instead of the right-hand side. Now, the first thing I would do is looking at where I'm trying to get to, I notice that I need to have a times cosine alpha in my answer. Well, I have cosine alpha to the 5th, so I'm just going to rewrite that as cosine alpha to the 4th times cosine alpha. So I have my cosine alpha at the end. That part I'm going to ignore. That is now just along for the ride. Somehow I have to take that sine squared alpha times cosine to the 4th alpha, and it's got to turn into that trinomial. If I look at that trinomial, the only thing in it is sines. So I'm probably not going to worry about changing that sine squared. I'm going to leave that there, because I know that whatever that stuff has to turn into has to be all sines anyway, so I'm just going to let it be. What I'm going to do instead is I'm going to concentrate on cosine to the 4th. Everybody's okay with that reasoning? Now, I don't have an identity that's going to turn cosine to the 4th into sines, but I can, let's see, we just rewrote that. I can rewrite cosine to the 4th as cosine squared times cosine squared and what does that get me? Well, I know using P1 I can rewrite cosine squared as 1 minus sine squared. So I'll do that. I guess I did it twice. I'll write times 2. Is everybody okay there? Now everything is sine squareds, right? So this stuff here has got to just turn into that. Okay, well, I have 3 things multiplied together and then 1 thing. So on the left, I have 3 things multiplied together, sine squared, 1 minus sine squared, and 1 minus sine squared. On the right, I have 1 thing. So reason would tell me, let's just multiply everything out on the left-hand side and should get me what I want. So I'm going to do that first. So to multiply those guys out, I got a FOIL. 1 times 1 is 1. 1 times negative sine squared is negative sine squared. Negative sine squared times 1 is negative sine squared. And then negative sine squared times negative sine squared is positive sine to the 4th. I noticed that those are like terms in there. I'll do my usual foiling cleanup. Yes, negative sine squared minus sine squared is negative 2 sine squared. So now I have 2 things multiplied together. So, okay, well, I mean, I got to multiply that through then, I guess. Sine squared times 1 is sine squared. Sine squared times negative 2 sine squared is going to be negative 2 sine to the 4th. Remember, we're adding exponents when we multiply. And then sine squared times sine to the 4th is going to be sine to the 6th. Again, adding exponents. And that is exactly what I had on the other side there. Now, had you started on the other side, the work would be ostensibly the same, but instead of foiling, you would have had to factor. And again, if I have my choice between foil and factor, I'll pick foil every day of the week over factoring. It's a much simpler process, but still doable for us if you had to if you chose to go the factoring route. Still doable. But if you run into that, like you do your problem and you end up having to do some factoring, there was probably means that you could make a different choice, start on a different side, or do something different at the start, could have ended up with a foiling problem. So if you get stuck and you're like, oh no, I have to factor this thing now and I'm bad at that, it's okay to just like start over and make a different choice and see if you can do it as a foil problem instead of a factor problem, if that's a weak point for you. If you're good at it, then no worries, right? If you're like, I'm a factoring wizard, that didn't scare me, then there's no concerns, right? You run in whatever you run into, and you're good to go. All right, how do you guys feel so far? Yeah? All right. So I passed out to everybody at the start a sheet that just says notes 3 on it or whatever. What we're going to do is I'm going to call on some random volunteers, not so voluntary when I call on you, to kind of help talk through what to do on these problems. So you probably want your notes sheet out that I just passed to you, as well as your identity sheet. So let's take a look at the first problem on the note sheet. What do you notice about the identity that's given to you on that first problem? There's no trigs in it. There's no sines or cosines or anything in it. What's that going to tell you? The identity sheet is worthless, right? It's going to be all algebra things that we have to do. Okay? My first volunteer is going to be Emily.
Oh my God.
What do you think we should do first? Which side would you want to work on?
I'm confused how this is set up. That's what, okay. The left side.
Excellent. I think that you'd be a crazy person to want to start with 2. Okay. Next up, what should we do first? It's all algebra things. We've already established there's no trig things in here to do. What would you want to do first? So that's not a terrible choice, and you can certainly get to the correct answer through that way. It's not the easiest route, though. What do you notice about those numerators other than they're the same? So when I see that, it looks like a difference of 2 squares. So I would choose first to factor. So if I do that, how does x squared minus 1 factor? What does it factor into? Remember the factoring pattern.
X squared minus. Stop talking.
Yeah, Anthony, you'll have your chance. Then Emily's going to be whispering in your ear the whole time.
X squared.
It's not x squared, though.
Oh, X.
Yeah. And what do you notice we can do now, Emily? We can reduce. Mm-hmm. Oops, that was supposed to be a subtraction symbol there. Now, what I've written is incorrect. So this right here is incorrect. I've written it incorrectly on purpose because I bet that 80% of us would write it as such. Emily, what do you see the mistake that I've made in going from here to here? It's hard to see the mistake. Yeah. That needs to distribute. That's right on. So really that second parenthesis still needs to be there, and then we need to distribute the negative through. And then if you combine like terms, we got our 2. Now, the only reason I worked this from left to right was because of the space on the sheet. Normally, I would do this vertically, but it is what it is, right? Emily, wonderful job. Thank you. You might recognize the second problem on this sheet is one that we already did in the notes, so we're going to skip that one and go to the back page. All right. Joey, you are, yeah, Tommy?
Maybe I missed it, but do we just put like what identities we use for like the 1, 2, 3?
So it's like it's more like the strategy. So like I did just factoring, reduce,
Oh, okay.
and then like I guess we combined like terms or something. I wouldn't ask you to fill that kind of thing in a test.
All right.
Yep. So the strategy is more about the meta things rather than the individual identities that we'd be using. Okay, Joey, which side do you think we'd want to start on, lefty or righty?
What?
Yeah, I agree. Again, I see on the left side, I see two things. On the right, I see one thing. Two is more complicated than one. Good. And what do you think we should do first? So cross multiplication is never something that we can do with an identity, but you couldn't use cross multiplication here anyway because you don't have one fraction equal to another fraction. So, right? Because here we have the sum of two fractions. So you can't cross multiply, even if you were able to, but you aren't when you do an identity problem. What else you got?
We reduce.
Well, the numerator is already 1. There's no reducing if you have a numerator of 1 that you could do. Sure. Let me ask you this. We have two things on the left-hand side, right, Joey?
Yeah.
And we have one thing on the right-hand side. How do we take two things that are added and turn it into one thing? What? Well, we have two things that are being added, and we want to turn it into just one thing. You got to add them, right?
Yeah.
Okay, what are the two things that are being added right now?
1 over secant x minus 1.
Yep, and the other thing is?
1 over secant x.
And both of those things are fractions, right? So what do we have to do to add fractions? Yeah, so that's what I would do first. So what would the common denominator be between secant x minus 1 and secant x plus 1? Okay. What if it was 1 over 2 plus 1 over 3? What would the common denominator be? 6, right? How'd you get 6? Okay. Let's do the same idea here. The common denominator would be minus 1 times secant x plus 1. Is that okay?
Yeah.
Just in the same way that with 1 over 2 and 1 plus 1 over 3, we had 1 over 2 times, or we want to have the denominator of 2 times 3. So we'll multiply the first fraction by 1 plus secant x, and the second fraction by 1 minus secant x. So far, so good. So I'll go ahead and write this, or do the multiplication, like combine the like terms and write this out. Oops. I'm a goof. Sorry about that, guys. Okay. So there we go. All right, Joey, take a look in the numerator. What do you notice we can do up there?
So if you cross out secant x minus 1.
Definitely can't, because this is part of an addition problem. You can't cross out just part of an addition problem. It's either the whole addition problem or none of it. What else do you got? Yeah. So what can add together? 1 and -1, right? That gets me 0. And then secant plus secant. Those are like terms. What do I get when I add those together? Nope. What if you add x plus x? Well, you get 2 secant x, right? Like x plus x is 2x. X times x is x squared, right? All right, I've tortured Joey enough for now. Cameron, let's take a look at where we're at now. What do you think? Let's take a look at where we're trying to get to again, right? Trying to get to this. Notice that, hey, all right, I got the 2. That's good. Now, if I look at that yellow circle, do you see any addition or subtraction going on in there?
No.
No. So what do you think is going to be my first order of business?
Multiply.
Yeah, let's multiply that denominator out, right? To start working towards getting rid of that. What do you notice that denominator is? It's that special difference of 2 squares situation, right? That's actually like strategy 2 that we're using. We're using running into that dots thing. All right, what's up next? I still have addition and subtraction going on now, right? We've traded 2 additions and subtractions for 1, which is good, but we still got 1 in there. How are we going to get rid of that?
Dividing.
Nope. We already foiled. So we want to turn that into one thing. You need to look at your identity sheet. When you see squareds in addition or subtraction, which group of identities are you going to be looking at?
Well, I'm not sure.
You should be looking at the Pythagoreans. Which of the 3 Pythagoreans have a secant squared in it?
P3.
P3. Now we have a secant squared minus 1 though, right? So if I take P3 and I subtract 1 from both sides, I get that tangent squared is equal to secant squared minus 1. So I'm going to say that. Okay? All right. I've tortured Cameron enough for now. Tomasino, you're next. So again, I've done a little bit more. Let's take a look at where we're at. We're still trying to get cotangent times cosecant. I have the 2. Now let's look at what else we have. We need a cotangent. Let's think about the stuff that cotangent is the same as. If I look at my identity sheet, cotangent's the same as cosine over sine, cosecant over secant, or 1 over tangent. If I look over here, which one of those do I have?
Would it be Q2, so secant, or cosecant or secant?
Well, I don't have cosecant anywhere over here, do I?
No.
I don't have a cosecant over here. What I do have is a 1 over tangent, though, right? Because I have tangent squared in the denominator. Do you see that?
Oh, yeah.
So if I just rewrite things, I'll just abbreviate that as RW. I can rewrite that as 2, and then I'll write 1 over tangent, and then I'll write secant over tangent.
How'd you get the secant over tangent?
So I took the tan squared and rewrote it as tan times tan, right?
Oh, okay.
So I have this piece that's the same as the cotangent. Can we put that someplace where we're going to be less likely to kick it over, since we've done it a couple of times now? So that means that everything that's left has to turn into cosecant somehow, right? Does that make sense, Tomasino?
Yeah, it does.
Okay. So let's start working towards that now. How do we want to try to turn secant over tangent into cosecant? If I look at the identities that it concerns secant or tangent, do any of those also contain a cosecant?
Q1.
Yes. So Q1 will allow me to write tangent as secant over cosecant. Okay. And let's talk about how we're going to reduce that. So I'm going to think about the numerator instead of just secant x. I'm going to think about a secant over 1. And then I remember that dividing two fractions is easy as pie. I flip the right, in this case the denominator, and then multiply. And what do you notice that's going to happen here? Which is exactly what we were hoping to get, right? So we used R6 to turn 1 over tangent to cotangent, but that's the end. We're going to skip the next problem because that's exactly the same as the one we already did in the notes. We're going to go move on to the last problem. Thomasino, I'm tortured you enough. Thank you. Ethan, you are next in line for the torture chamber here. Which one of these do you want, or which side do you want to start with?
The left.
Okay, you can do that. And I see there, to me, they look just about the same, right? I both have like two things. Here I have something divided by 1 plus something. And on the right, I have something times something minus something. I don't know, they seem about the same to me. All right, so we have this. And what do you want to do first? Let's look at what we want, right? Notice that we want something cotangent times something, right? We have a cotangent in the numerator. So if we just kind of rewrite things, I can take that cotangent from the numerator and just move it out front by itself. And I have that part done. So now I'm going to try to do this. Got to turn cotangent u over 1 plus cosecant u into secant u minus tangent u. Okay with that plan? Okay. What are your ideas?
Change the cotangent
Into 1 over tangent.
1 over tangent.
I could, but I mean, like, I don't know that that's going to be like super productive. I know I have a tangent here, but it's not a 1 over tangent. So I probably wouldn't go that route, although it's not incorrect. I don't think it's going to be helpful. Here's your hint. And it's not on your identity sheet.
It's not.
It's not.
So,
So when I look at the denominator, that looks like an a plus b to me. What's almost always going to be a good idea to do if you see like an a plus b or an a minus b? Yeah, I'm going to multiply by, the a minus b, right? To the top and bottom. Now I'm going to be a little bit careful here, though. If I look at my identity sheet, I want to find the thing with sine or cosecant squared and 1 in it. Which identity is that?
P2.
P2. Am I going to want cosecant squared minus 1, or am I going to want 1 minus cosecant squared? If I look at my P2. Yes, that is what I would want. So I want to make sure that when I multiply by my a minus b, that I have the minus attached to 1 and not to the cosecant, just to make my life a little bit simpler. Now, Mr. Kulik, this looks like b plus a then and a minus b. who cares, right? If we're adding two things, it doesn't matter the order. Everybody's okay with that? If you're subtracting, it absolutely does. But the adding, it's okay. Are we happy so far? Okay, let's see what we get when we FOIL that stuff or multiply that stuff out. All right, so I still got that cotangent stuck out front. And then I'm going to have cotangent times cosecant minus 1 over cosecant squared minus 1. And Ethan's already identified, oops, forgot a C there, that we can use P2 to write that cotangent or cosecant squared minus 1 as cotangent squared. So far, so good. What do you notice now? Yeah, we can reduce a cotangent, right? Mm-hmm. God bless you. God bless you. You're welcome. Now, the next trick you'd have to employ here is a toughie. And I want to be clear about this next trick. It only is going to work when your denominator is a single term. It does not work if your numerator is a single term and your denominator's got addition and subtraction in it. This only works if your denominator is a single term. But I can break that into two fractions that both have a common denominator of cotangent. Now, why would I want to do that? If you go back and look at what we're trying to get to, it's the difference of two things, right? So I've spent all this time banging away at that fraction to try to change it from a fraction to subtraction of two things. But we've gotten that much out of it. So that's good. That's good progress we've made, right? Because now we have subtraction. All right. So let's look for some identities here. This thing eventually has to turn into secant minus cotangent. I'm sorry, minus tangent. So if I look here, 1 over cotangent, that has to turn into tangent, right? That's great because I have an identity to do that, right? That is R3. So I got that piece nailed down now. Do I have an identity that's going to change cosecant over cotangent directly into secant? No. Do I have an identity that changes cosecant into something with a secant in it? Or cotangent to something with a secant in it?
Yeah, you can change both.
Look at Q2.
Is the one that
Yes. So I can replace cotangent with cosecant over secant. And I'm going to do that same like multiply by the reciprocal trick that we did before. So we're left with just the secant, and that's now everything I need. I would like to point out to you guys that I think that if you had started on the right side here, this would have been much easier. Because you probably could have just started by writing secant as 1 over cosine and tangent as sine over cosine, make a common denominator already, and things I think start looking pretty nice pretty quick. But that's okay. What we did was fine. Got us there. All right. For homework, you guys should be working on numbers 47 through 54. I think that's 8 problems. We'll do some more of these next time. Again, it's probably not instantaneously easy yet. The hope is, though, that after we're 2 or 3 steps in, you kind of start seeing your way to the finish line. Because you can start seeing, like, okay, I can see what to do next. I can see where this is heading. That's kind of where you should be at this point. You probably can't look at the problem from the start and see you're all the way to the finish. But if you can see yourself like halfway through and then reassess and then see the rest of the way, you're in very good shape. Okay?